Next, we have Ken Duda, the founder, CTO, and senior vice president of software engineering at Arista Networks. He's a pioneer in high-performance networking software and lead architect of Arista Networking EOS, a modular operating system for all Arista network products. He's also the co-author of the network virtualization specifications, including VXLAN and NVGRE. Ken was also the first employee of Granite Systems and led the software development for the Catalyst 4000 product line after the acquisition by Cisco. Ken has 3 simultaneous engineering degrees from MIT and holds a PhD in computer science from Stanford. Ken, welcome, and please take it away.
Oh, thank you. Thanks for that nice introduction, JK, and very grateful for the chance to talk to you all here. I must admit, it was a little bit unnerving hearing Andy's disclaimer, because I feel if anybody needs a disclaimer for this show, it's me. So I will come to you here as a humble vendor, trying to build products, some of which involve P4 and programmable data plane devices. I am not an expert in this area, but we've got some experience on the ground with actually building and selling products based on this technology. What I wanted to do at this time was share with you part of our journey to give you just a kind of a taste of what our view is, what we see from the point of view of trying to build and sell commercially viable networking products that involve programmability. So what are we even talking about here? What is the programmability? Well, let's see, we've got P4 in some of our ASICs, especially Tofino 2 from Intel, obviously. We also have programmable devices using VHDL, FPGA-based devices, obviously a little more old school there. And then, of course, P4 gives us much higher performance because it's specialized to the networking use case compared with VHDL. The FPGA obviously is completely general purpose stuff, but there's a long history there, of course, of and FPGAs have been around a long time. So who's doing this programmability? Who's taking advantage of it, actually creating programs in P4 or VHDL? Well, mostly it's us, I mean, the switch vendor. So we're building features for our customers using these technologies. But we do have some cases of sophisticated customers doing development directly themselves, as well as development partners, professionals using these tools to create products for yet their own end customers. So I thought those were particularly interesting use cases and illustrated what is important about network programmability. So why? Why build a programmable data plane at all? And so and how is it useful for us, our customers, our business? And that's what really this talk is about. So if you look at the promise of ASIC programmability, I've encountered this promise many times in my career, going back at least to, I don't know, 1998 or 1999, where engineering teams have told me, hey, we're going to have this new programmable chip. It will be more flexible. Customers will be able to deploy new features into their existing installed base of switches. It's going to lead to lower costs because you don't have to pay for features in the chips that you're not using. You can reduce the cost of the silicon, the power it consumes, the risk of having unneeded features leading to bugs. It's all going to be more efficient because you'll have one hardware SKU, sort of one switch model you can plug into your racks and use that for many different use cases, loading different programs in the programmable units to evolve its purpose over time. We'll get faster development because you can bring your new silicon to market faster because the silicon development is now decoupled from all of the individual layer 2, 3, 4 features that you're trying to build. They can be added in later through the programmability mechanism. And also this enables strategic opportunities for our customers. Customers can gain proprietary advantage by creating their own custom IP on top of our programmable platform. This all sounds pretty good. This hasn't really been the reality for us. The problem is, each of these has its own set of problems. In terms of the flexibility, being able to deploy new features into your existing network, the problem is it takes years to deploy a new feature architecture. So for example, with VXLAN, Arista had the earliest fully accelerated, hardware accelerated VXLAN implementation in the industry. And we built it because a lot of customers were telling me, hey, this VXLAN thing sounds great. We want to deploy this and so on. Turned out they didn't really want to deploy it, at least not yet, because They need a whole ecosystem around it. They need a good control plane for it. They need it integrated into VMware and OpenStack and in the Linux. They need it in their sniffers and in their extra hops and in their every tier of the network needs support for this. And it just takes time to build and deploy all of that. It actually took multiple silicon generations until VXLAN was really fully deployable. By that time, your hardware is end of life, and so it hasn't actually been that important. I think we saw something kind of similar with INT, that to really deploy INT at scale requires whole INT regions of the network and standardized collectors and a bunch of stuff that just made it take enough time that by the time you can deploy INT, new switch silicon, fixed function silicon already has the support you need. In terms of being lower cost, the problem is that since the sort of fixed function stuff can absorb all the high volume features, the programmable stuff is driven into lower volume use cases. And if you're into low volume use cases, you can't drive the kind of volumes that lead to actual lower costs. So we haven't seen that to be true as well. In terms of efficiency, around having only a much smaller number of hardware SKUs, it turns out that different roles and different use cases in the network also have diverse port configurations in terms of the transceiver types, cable types, link speeds, number of ports. Is this a modular or a fixed function box, uplinks, QSFP, QSFP-DD, OSFP? You end up with SKU diversity no matter what you do here. And so we haven't seen a big improvement there. In terms of faster development, well, that wasn't our experience. So the ASICs certainly didn't come to us any faster than they were coming from more fixed function competitors. And what we actually saw there was really impressive strategy, I thought, from one of the dominant ASIC players who structured their roadmap in terms of these sort of overlapping product cycles, where one product family introduces the newest ASIC process, the newest technology, so going just to smaller, higher integration density. And so you ask yourself, who's going to adopt that? Who's the early adopter for the very fastest link speeds, the densest integration? And the answer, of course, is the hyperscale cloud. So, okay, so in that line of ASICs, they only build the features that the hyperscale cloud needs in their data centers in the tier 0, tier 1, tier 2. And then the second generation goes ahead and integrates in all the features and tunneling and security and all the stuff that enterprises need. And that does take longer to get to market, but the enterprise market wasn't ready to adopt it anyway. And so this ends up meeting the market needs, I think, in a really cost efficient and it's sort of a good time to market kind of strategy. And then that leaves us with, it enables customers to be more strategic and gain proprietary advantage through their own custom IP. But can they really? How well does this really work? And so from the end user's point of view, it ends up being very challenging to create data path features, to exploit data path programmability in network switches. We've had actually quite a bit more luck getting our hyperscale customers to adopt our control plane and management plane programmability, running their own software directly on our switches, either alongside or replacing our software. It's been harder on the programmable silicon side, because how do you divide the engineering between us, the system vendor, and the end user? What the customer always seems to want here is, hey, I want your standard switch features, but plus my special tweak, right? Like they don't want to start over and like be implementing layer 2 bridging from the ground up, right? So how do we enable customers to do that without sort of sharing our entire P4 source? Because we've got a lot of what we consider to be trade secrets and valuable, our own valuable proprietary IP in the P4 source. And even if we do that, fitting a P4 program into an actual ASIC, it's a major challenge. Getting all the features in there, you've used every last hardware resource, and then trying to train the compiler through annotations to actually fit your design in. And then for the customer to then try to piggyback on top of that is just a very big challenge. The compiler targets the whole pipeline, right? So that when you're compiling a P4 program down into Tofino, it's compiling across all 12 stages of the pipe. And it doesn't sort of leave things free for somebody else to then go add a piggyback program onto. It's hard to reserve stages without really constraining how our designs work. I personally feel like there's some opportunity for some kind of fundamental improvement here, some way to I sort of joke as, we need multics for the switch ASIC, right? Like, because CPUs used to be hard to share, right? I mean, remember 1958? You had to go and rent time on the big mainframe and all 4 kilobytes of memory and put your program in there. When your program was running, no one else's program could run. And then these crazy folks in MIT in 1964 or something came up with this idea of multics. We could have more than one program running on the same CPU at more or less the same time. And I think P4, to really enable this promise of customer programmability, needs something along those lines, so that to help us share the hardware device with our code and plus the customer's code. That said, I want to go ahead and highlight some of the use cases we've encountered. And the purpose here is really to share with you what we found to be useful. I hope this doesn't come off as a product pitch. That's really not my intent here at all. One of our volume use cases we're very happy with is using P4 to extend and really change the behavior of our switches to serve as a gateway to bare metal servers in the public cloud. So you've got a public cloud with a data center network, top of rack switches connecting to all the servers in the public cloud, running a bunch of customer VMs, customer workloads. But then some customers want to install their own physical hardware in the public cloud. So the physical hardware shows up, the tenant controls the physical hardware completely, including the networking stack. And this creates a problem, like you don't want to connect the tenant's hardware directly into your data center fabric. They're supposed to be in a customer specific overlay. Where does that mapping take place? The mapping, which is done in the vSwitch, right, for the VMs, mapping customer execution into overlay networks. Where is that for the bare metal hardware? And the answer is in an Arista device, which has a Tofino ASIC in it, which essentially plays the role of the vSwitch for bare metal workloads. And the key features here are being able to kind of repurpose all of the lookup tables to have tons of NAT translations. There's a major amount of NATing going on inside these networks, and tons of tunneling because every customer is in their own set of tunnels for their VPCs, their own overlays, using, of course, non-standard tunnel encaps naturally. So there aren't very many platforms that can do this, and Tofino is one. So this is where we found this kind of programmability to be very useful and create a nice opportunity for us to meet a customer need. Another application is stateless load balancing. People have experimented with using standard layer 2-3 switches as kind of stateless load balancers, basically by ECMP or lag hashing incoming TCP connections across a bank of servers. The problem with those designs is that whenever your set of available servers changes, your hash function scrambles the mapping of flows to servers, and you wind up basically trashing every in-progress TCP connection, which customers don't like. Imagine that. So what do you do about that? And it's tricky, right? Because you end up quickly needing kind of a full layer 4 flow table in hardware, and the number of flows can be very large, and it just doesn't work very well. So we have this, I don't know, is hacky the right word for it? This hacky approach to provide extremely high performance, stateless layer 4 load balancing. And the way it works is a packet, it's maybe a TCP SYN, or maybe it's not a SYN, maybe it's an existing connection. Some packet comes from some customer out there, hits your data center edge. Data center routes it down to our load balancer. That's step 2 here. The load balancer then just hashes the packet and picks whoever's currently serving that hash bucket. Maybe it's load balancer 1. VXLAN encapsulates the packet and tunnels it to load balancer 1. Gets to load balancer 1 here in step 4, and if it's a SYN or it's a packet on an existing connection, that's great. Server 1 processes it and off you go. But what if your hash function is scrambled recently? And this packet here is on a connection which is actually being handled by server 3. And until recently, the layer 2, 3, 4 header of this packet would have hashed to server 3. But because of a change in server availability, the hash function changed. And now it's hashing sort of incorrectly, or at least unhelpfully, to server 1. Well, what server 1 is going to do is send a reset, right? And the connection is going to get shut down and the client has to reconnect. Well, not with our hack. So the hack is right here. We hack server 1 in the host side to, instead of sending the reset, why don't you just return that back to us? So it just switches the header in the VXLAN and sends a packet right back to the load balancer saying, I don't know what this is. I don't think this is for me. Return to sender. So it sends a packet back to the load balancer, and it VXLAN tunnels to the load balancer again. And the load balancer says, well, that's funny. I guess server 1 didn't want this packet. And then who was most recently serving that bucket before server 1? Oh yeah, it was server 3. So we maintain history for each hash bucket in the load balancer. We maintain a history of which servers were serving it, so that if server 1 doesn't like the packet, maybe server 3 wants it. And so then it redirects the packet to server 3. And this way, all of your flows survive a change in the hash membership, in a hash set. So new servers can come online, servers can go offline, completely non-disruptively. You just have to keep enough history so that your packets can eventually wander their way to the correct server. I sometimes affectionately call this mechanism a DDoS attack multiplier. Wait, did I just say that out loud? So obviously there's issues in doing this well, security implications and so on, spoof prevention and all that to get a complete solution here. But this is pretty cool. We did this in partnership with a tier 1 SP, and they're using this successfully in their to load balance across their web infrastructure. So that's kind of cool. We also have a DDoS mitigation solution. This is with a Cloud Titan partner. It's replacing A10 plus a router, so it's a extremely expensive solution they have in place right now. We can do this much, much more cost effectively using P4. It's kind of, this is not yet actually deployed, so this is sort of work in progress here. We've demonstrated this actually does work. We did a POC for the customer and they're considering their options. But the idea here is that the external system detects a DDoS attack. It informs our box. 7170, this is the Arista switch with the Tolfino ASIC. It employs a 2-level policing towards the service VIP, both per flow and also aggregate to that VIP, with a permit list of known good sources. Then for things that are not known good, we implement a TCP SYN challenge. And the simplest version of this is literally you just use a Bloom filter to drop the first SYN. So a SYN shows up, you just drop it, but you mark your Bloom filter as, well, permitted if this thing shows up again. And then when the end station retransmits it, you then accept it. And at this point, you're on the known good list. Boy, I gotta say that one does. This is actually what their current solution does, believe it or not. And I'm sort of amazed this even works. Don't the bad guys just send 2 of each packet and get right through this thing? But in any case, we have demonstrated that we can implement SYN cookies in hardware as well. So that's pretty cool. And that requires now keeping per flow state or else having the exact same SYN cookie algorithm as the server. But either way, yeah, so you can implement a pretty good DDoS protection using this as well. And then finally, I'll give you an example, which is actually layer 2-3. So one thing you might notice is these examples were all layer 4 through 7 stuff, but we have a layer 2-3 example as well, which is MapT. And MapT is this, it turns out IPv6 headers are so large, you can actually tunnel traffic using the v6 address essentially as a tunnel header, which is kind of amazing. Anyway, so the idea here is to tunnel v4 traffic over a v6 core. So the v4 traffic shows up at a border router and it will rewrite, not encapsulate, but rewrite the v4 header to a v6 header, encoding and then route the packet using the encoded v6 destination across the v6 core until it gets to the v4 edge and then it gets translated back on the other side. This is a very efficient way of running v4 over v6. Doesn't have MTU problems and whatever. But you do need some fancy header field extraction, some spoof checking, some kind of weird rewrites. And some of our MSP customers in cable space are big fans of this approach. And so we were able to implement this on our 7170 using Tolfino when our ASICs, fixed function ASICs in our volume switching and routing platform simply didn't have support for MapT, and our MSP customers are big fans. So this is a good example of actually being able to take a feature to market early because we had the programmability support. But of course, none of these examples involve end users actually making any changes themselves. And we've had success there in our FPGA-based switches, where we provide, let's see, how am I doing on time here? We provide the basic IP blocks to the end user for MAC layer, extracting packets out of serial links, L1 muxing, L2 muxing, packet insertion into serial links. And also we have L2, L3 switching cores. We provide the customer with a tool chain and SDK, just as library for creating a CLI for managing some state on the switch, and a library for talking to the FPGA on the switch. This all works within the context of our switch OS. We obviously provide the switch hardware with various FPGAs, various numbers of ports. And some of our platforms include a Jericho 2C as well. So you've got one device has L1 muxing capability, FPGA programmability, and a very high performance switch router function as well. And we've done some cool things with this. I'll skip over this. The customers have done some cool things as well. So this is where we have some good examples of customers actually implementing extensions to the switch. This is mostly in the high frequency trading space because these are some of the lowest latency switches in the universe. So they're popular with the algorithmic traders. Customers have their own risk management controls. This is FPGA code that watches orders flying by and figures out how much capital is at risk and shuts down the connection. Some of our customers have lost amazing amounts of money because of just they're trying to move fast in their algorithms, and sometimes there are bugs. And boy, these guys have figured out ways of creating some very expensive bugs. So they have risk management controls in the FPGA itself to try to get a grip on some of those. They've actually deployed their own trading algorithms directly in box for the absolute lowest latency. And we've built a multi-FPGA box to enable more elaborate trading strategies. And there are also some federal applications of this FPGA switches, which I don't know the details of and won't be going into here. So that's where we've had some real customer uptake. We also have, here's one example of a customer, Netnode, which built a secure NTP server, very high performance, low jitter. And this is open sourced. And we sell the switches to Netnode. They run their applications on the FPGAs using our timing blocks. And then can add very accurate timestamps to packets, which is useful for understanding where the latency is in your low latency trading system. We also have third-party engineering partners that have built products out of our devices. Enix is a specialty provider that's built a MUX device for accessing a microwave link. You may know that if you're going a significant distance, microwaves are preferred by the low latency traders for cross-market arbitrage compared with fiber, because the speed of light in free space is about double the speed of light in fiber. So they can literally get their market data from London to Frankfurt faster using microwaves than they can with fiber. But you probably also know that microwaves have this problem that sometimes it rains and the link isn't 100% reliable. And so the NX MUX directs packets over a combination of microwave links and fiber links using finance-specific compression and deduplication to give the customer the lowest latency possible service at high reliability. And they're using our devices for that. And then Nextera makes a software-defined digital video service with features like transcoding, picture-in-picture scaling, compression, color correction, and SRT to SMPTE 2110 gateway. And all of this is integrated with layer 2-3 switching and routing, multicast, and all the QoS requirements of a digital video production network. And that was all made possible by embedding all of these sort of video algorithms into the FPGAs in our device. So that's an example of some pretty significant product engineering done by a partner taking advantage of FPGA programmability. And I mentioned these to kind of highlight that we have more uptake of customer programmability in the FPGA space than we do in the P4 space, which in a network device is kind of ironic because that was sort of like the reverse of the intent, right? So anyway, the takeaways here is that innovating in the core L2, L3 data path is hard. It takes time. So basically the ASIC development delays don't really affect deployment very much. Sometimes you can get a jump on things, but that's been rare in our experience. The programmable silicon is more useful for layer 4 through 7 and sort of niche use cases. But we lack a model for joint development of P4 that makes it easy to preserve all the layer 2-3 features. But the market size here is greater than 0, so it seems like something worth trying to tackle. And thank you for your time, and I'll be happy to take any questions.
Thanks a lot, Ken. Walking us through the many insights you have collected over the last many years of experience on P4 Tofino development, and at the same time, giving us some nice brief on the cool applications you actually built and run in action in actual systems. So with that, there are some questions in the chat. And the first one is that sort of table scale on Tofino-based Arista switches in the max table size, whether it can actually fit full internet tables and similar to other fixed function devices.
Yeah, so boy, this is embarrassing. I don't know the exact max table size, and as the questioner correctly points out, it depends. Max table sizes depend critically on the P4 program you're running, because there's a lot of chip resources that you can use for routing or for other features. The challenge is that we haven't gone down this path. The problem is that anywhere where you have the requirement for service provider scale routing, you have a lot of other requirements as well. And basically, we have requirements for tons of different transceiver types for a large modular platform. It's big multi-chip core router sort of device. So we haven't seen fit to try to bring Tofino to the service provider market. We've really been focusing on the Jericho lines. The Jericho has the multi-chip fabric, the non-blocking deep buffers. The off-chip DRAM buffering is also very important there to get very good throughput in the presence of a multi-chip network. Without the off-chip DRAM, you have a lot of problems with elephant flows on a hash fabric and leading to lots of loss. So the Tofino doesn't give us any way of putting our chip buffer into DRAM. So I think there are a lot of different aspects here. The other thing I would say is that the route scale actually requires off-chip routing tables in the largest use cases, talking 30 million routes, that kind of thing, where you've got multiple customers taking multiple copies of internet routing table and that sort of thing. So it's there's no chance that with on-chip routing you could really meet the full requirements of the service provider market. So I hope that answers the thrust of the question, even if I don't know the exact number. I apologize.
I do remember, excuse me, some of the table scales, high-level table scales are published in the Arista website for different profiles. Actually, I found it really useful because it's the same hardware, but based on different people profiles, different scale in terms of layer 2 and 3 Acker. So yeah, I think that is some amount of resources that the audience can check out in the Arista website. And then with my Intel hat on, there is a number of attempts, actual systems being built by for some type of PRC cloud providers with some ODM vendors to have some hybrid system between Tofino and FPGA and external HBM or DRAM memory, using FPGA as a kind of memory controller, extending the traffic management system buffer, or using the external memory as a buffer, or actually extension of the lookup table. So there is a number of talk actually in the program of this workshop. So please check out those contents that may answer some of your questions from the community.
Thank you.
Second question, any plan to open up Arista switches to allow your customers to load their own P4 program?
Oh, we already do this. So you can load your own programs into Arista switches.
There is a final question. The speed of the light limitation in fiber, some companies have started to test glassless fiber to improve the speed. Any comment on that part? Well,
this is obviously a specialty use case. I think most of us aren't particularly concerned about the speed of light in fiber, but that's interesting that's going on. Sorry, I don't know anything about it. That's great.
Okay.
Comment.
Great, thanks. I think we still have a couple of minutes, so maybe I can share a couple of questions I wanted to ask. One is your observation on the L2, L3 versus now L4, L7 and niche use cases. I agree with you, but I definitely see the having programmable data plane also in the switches motivating the entire industry and then silicon vendors to move more into the programmable data plane. So today we have the mixture of fully programmable data plane versus half or a fixed function devices coexisting. That kind of fundamentally slow us down in terms of innovating L3 forwarding features. But what do you expect that when we will be able, when we will be able to actually innovate fully in L2, L3, it will be another decade, or similar to your analogy to the CPU cases?
Yeah, so I guess, well, this is just one guy's opinion here. So first, you made a good point. Actually, a lot of the ASICs, that aren't usually thought of as being fully programmable, aren't necessarily P4 programmable, actually are pretty flexible. Like there's a fair amount of stuff you can do in a modern ASIC from any of the large vendors in terms of reprogramming the way that keys are extracted from headers, the way, which tables those keys are looked up in, how you resolve the results of multiple table lookups, the rewrite engine for packet manipulation. So so you're actually made a good point there that programmability has been going up generally across the industry, whether or not it's sort of complete or sort of P4 based. So that's very true. In terms of innovation at L2, L3, my observation here is that it's hard. I mean, it's just sort of fundamentally hard to deploy new data path features at L2, L3 because there's so many dependencies that you need all of your systems at that level of your infrastructure to be aware of. You need to architect your networks with those features in mind. The way that provisioning, observability, your network packet brokers, your tools and analysis, endpoints, packet recorders, all that stuff has to deal with it. And so I think that it just takes time. I thought it was very instructive. I mean, VXLAN had a major impact on the way enterprises build their data center networks. I mean, there's been an enormous change from being L2 networks or L3 networks to now being almost every enterprise is building L2 over L3, and L3 core carrying L2 as a service over it. So, but that took, I don't know how much, I think we were first really seeing that in scale around maybe 2019, 2018, 2019. So it took like 8 years or something. So you get sort of multiple silicon generations to really adopt something like that. And if we're talking about experimentation, I mean, we have platforms for experimentation. If someone's going to go into a research lab and university and wants to fiddle with something, that's not a problem today. So I sort of feel like what's holding us back in terms of the amount of time it takes to innovate, like you said, it's not really a technology problem. It's really just the number of things that have to change. It's a human problem. It's a layer 8 and 9 problem. It's just going to take some time. That's my belief.
Thanks a lot. That's a very good kind of homework for the community, and a lot more to do and innovate actually. But I think we are in the right path. It's a kind of, I feel, a matter of time, but we are all marching into that direction. So thanks a lot for sharing your insights. Let's conclude this particular keynote session with this awesome speaker, Ken Duda. Thanks a lot again. And
thanks, JK, and thank you everybody for your time.
Thank you very much.